Okay, so you have understood systematic and random error. Okay, just to give you a quick picture to show this. True value is on the left for systematic error. You can see we're supposed to get this, but all the value measured is here. So this is a systematic error. Problems are normally due to instrument and cannot be improved or rectified by taking average. Okay, this one is random error. True value, the orange is here, but the measured values are all over the place. Can be here, can be here. So this one is normally due to human error. Okay, so in this case, taking average improves accuracy and precision. Whereas for this one, average only improves precision. Then you might be thinking to yourself, teacher, ever accurate and precise, not the same thing. No. Let's look at accuracy and precision. Okay, so precision here is the smallest division that can be measured by an instrument. Okay, so we can kind of increase the precision a bit by increasing a decimal point. So this precision is normally related to decimal point or smallest possible reading. Smallest possible readings. Okay, so we can also use average to increase the decimal point. Okay, I'll show you an example later. Accuracy is how close the values are to the true value. Accurate, correct, headshot. All right. So let's look at these two examples. Let's say you have two students that measure the same glass marble with different instrument. One student uses a vernier caliper. That's why you can see they all have the same precision. 2 decimal point, 2 decimal point, 2 decimal point. So these are all same precision because of the decimal point, 2 dp. All right. Whereas the second student, student 2, uses a micrometer screw gauge. And the micrometer screw gauge, you can check, they will all also have 3 decimal point for cm. What can you comment? Well, if the true reading is 2.5, then they are both accurate. Okay, so let's say, for example, if the true reading of the marble, if true reading is 2.500 cm, then they are both fairly accurate, very close to 2.50. Okay, but student 1 is less precise than student 2. So one comment. Student 1 and 2, they are both accurate, but student 2 is more precise. You know how there was this objective question where we say if we take average, we can improve the precision? Can. So whether this one got systematic error or not, I don't know. I don't know until I know the true reading. In this case, there's no systematic error because I have reading bigger than and smaller than 2.5. But if they never give me the true reading, I don't know. Okay? Just like if they never give me this true value, I wouldn't know all of this is on one side of the true value. Okay, but how do we increase the precision if, let's say, you are stuck with the vernier caliper? Okay, so example, we take the average diameter of this vernier caliper of the student 1's reading. So I will add up all these values and find the average. Okay, so after pressing calculator, this is my new diameter reading, 2.498. Okay, so I added up all the values, all 5 readings. Okay, and then I divided the answer by 5. So I get 2.498. I'll write that down. D will be equal to 2.498 cm. So you can see I have increased extra 1 decimal point. So by taking average, I level up the precision. Increase. Better precision. Greater precision. Okay? So in short, precision is about the smallest possible reading. Of course, it is limited by your instrument. Okay? Different type of instrument can have different type of precision. But you can do a little bit of statistic manipulation and say that we can increase 1 decimal point of the precision if average is taken. Only 1 lah. Okay, so for example, if I took the average of this vernier caliper, then I can match student 2's precision. Of course, student 2 can say, I can also average my 5 reading and get 4 decimal point. Can. Okay, so we can level up the precision if needed by taking average. And normally that is a better experimental method. We say a reading is accurate because the reading is close to the true value. Okay, we identify systematic and random error. Let's say, for example, your reading is not accurate. Is it due to random error or is it due to systematic error? Systematic error we can address. Random error, we may need to train the student how to do experiment or tell the student to pay more attention. Okay, so let's look at some past year questions now. This is from MJ19 paper 1-2. It says here that 2 quantities P and Q are directly proportional to each other. So if they are directly proportional to each other, this means that you should get a straight line, because you see experimental results are taken of a graph of Q against P. Okay. So we plot out a graph of Q against P. Now, if you think about Q and P, if P and Q proportional, you should get a straight line passing through the origin. Okay? Which graph shows random errors in the measurement of P and Q? So if there is random error, right, it means that the plots are either above and below the point. So this graph, this black color graph, this one is true value, the true graph that we want to see. Okay, so B is this. If there's random error, it means that sometimes you get reading above the true graph line. Sometimes you get reading below the true graph line. So in this case, the answer is C. But you wait first. I explain a few things. This one is anomalous reading. Anomalous means 无端端 for no reason. Suddenly got this point here. Hello, excuse, are you lost? Go home point. Are you lost? So this anomalous point normally is due to human error. Is it random? Yeah, it's fairly random, but it's not everything random. So this is anomalous point. We normally will classify as random error. But this is just human error. Okay. B is just a curve. So I also don't know what is going on in B. I'm just going to put question mark. Whereas D, you look at this, very interesting. If I move this line, you see this is the line that I get from the graph in D. If I move this line downward, it is directly proportional. So the line is supposed to be here. This is the true value. But this is your experimental value. This means what? Your experiment value is always bigger than your true value. Your Q is always bigger than the true value. So this one, part D, is a type of systematic error. Okay, so I repeat. A is anomalous point. Is it random? Yes, but only random for this point. The other points are okay. B, I don't know what happened. Maybe check equation. Maybe plot wrong graph liao. Maybe got calculation problem. I don't know. Maybe supposed to square something but didn't square. Okay? Check equation, calculation table. So I guess this is also human error. Okay? Whereas for C, this is a type of random error. Random. Sometimes you get reading above, sometimes you get reading below. Okay, whereas D is a systematic error because your experimental value is always above. Okay, all right, let's look at another question. This one. Okay, question 7. Same year, same variant, Major 19 paper 1-2. A man 75.2 kg. So this is his mass. This one, immediately I can draw this out as true value or the actual value. Okay, uses a set of weighing scales to measure his mass 3 times. He obtains this reading. Hiya. This is obviously systematic error, right? He's supposed to be only 75.2 kg, but he stands on the weighing scale and the weighing scale thinks that he's 80 kg. My dude. Ayo. Okay, anyway, which statement best describes the precision and accuracy of the weighing scales? Okay, let's go. Is it accurate? No, I miss it. You see this one. This one is not accurate. Okay, so it is precise and it's accurate and then plus minus 0.1 kg. So definitely you can tell that the precision is 1 decimal point because all of this reading 1 decimal point, 1 decimal point, 1 decimal point. So from here I can tell that the smallest reading, which is related to precision, is 0.1 kg. Okay, so it is precise to 0.1 kg. But is it accurate? No, teacher, 5 kg difference. 5 kg. That's an entire bag of rice. Okay, so the answer is D lah. Okay, so it's not accurate compared to the true value. So this is for this example. Okay, in the remaining part of this video, I'm going to work through 2 examples that involve calibration curve. Okay, so when we talk about calibration curve, we talk about a graph that measures, that has something to do with scaling at the side. But if you may be thinking, I have no idea what to do, don't worry, you can infer from question. Okay, so let's read the question first. We have an analog ammeter. Analog ammeter is the one with the needle one. Okay, the ammeter with that needle pointer. Okay, this is analog ammeter. Okay, got needle one. But this one is a uniform scale. Okay, so following prolonged use, okay, after much use and abuse, the pointer does not return fully to 0. Uyo, meaning the pointer cannot go back to 0 already. GG, this needle cannot go back to 0. When the current is turned off, the meter has become less sensitive. Okay, we got so many issues this one. Okay, so the meter has become less sensitive at higher currents than it is at lower currents. So this is issue number 2. The sensitivity change. Okay, so less sensitive here also means less precise. In other words, the scale are closer to each other at higher readings of I. What that could look like for this is, let's say for example, I look at this one. For large value of current, maybe now my scale is like this. Here less sensitive, so perhaps instead of 1 being here and 0.8 being here, your 0.8 will have to move. Maybe your 0.8 is now here. So now this part is to represent 0.2 compared to this part. Whereas in the beginning, 0.2 is more sensitive. Okay, maybe this is 0, this is 0.2. So your scale doesn't have to be uniform. In fact, sometimes it may not be. Okay, so let's go back to this one. It says that it is less precise at higher currents and pointer doesn't return to 0. Okay, the easiest one to address is issue number 1. Pointer does not return to 0. If the pointer does not return to 0, this means that when there is no current, issue number 1, when there is no current, there is still reading. Okay, so in this case, I need to make sure that the graph will show that that I already know that, oh, when there's no current, the reading doesn't count. Okay, so see here. Let's say we look at this graph. It is the graph of scale reading against true current. So how to read the graph? This one, for example, when the current is, let's say this is 0.1 ampere, your scale reading is 0 degrees. Meaning to say, this meter, the meter that we are talking about right now, I'm just going to move it to this side for you to see. It means that when there's current, this reading is still 0. Cannot be right. Scale reading cannot be 0. Okay, so this kind of reading is out. When the current is 0, scale reading is not 0. So this 2 is automatically out already. It should have reading. Okay, so this is out, this is out. Because when there's 0.1 ampere current, this reading should not be 0. On the y-axis, here as well. Okay, next. So now we got these two beautiful graphs. When the true current is 0, so at this point, my true current is 0. Okay, I equal to 0. But the scale reading not 0. This is what we want. It says here, no current, still got reading. Nah, no current, still got reading. D also, no current, still got reading. So this is issue 1 settled. This is issue 1. This is issue 1. This problem here. The best one is actually to have the graph passing through the origin. So this one is actually a systematic, which is also a 0 error. Systematic error, also known as 0 error. Okay, now the next thing to look at is the graph. Okay, so if I check the curvature of the graph, this one is decreasing gradient. This one is increasing gradient. This is to represent the second problem. So you see the second problem here. It says that the meter has become less sensitive. Less sensitive, besides less precise, it also tells us that you need large changes in current to create a small change in scale reading or needle deflection. So think of scale reading as your needle deflection. Needle deflection. Okay. That's why right now, when there's current, there's no needle deflection. But you check the gradient. If we're talking about large current, right? Large current will be on the tail end here, right here. This is the tail end. You see, our current increase a lot, here to here, the delta I. But the deflection is only teensy bit. Let's compare to option D. Again, we try to take roughly the same delta I. So here to here, you can always use your ruler when you do MCQ questions. Okay, here to here, you can see almost comparable delta I. But here, larger deflection. This is small deflection. So small deflection means less sensitive. That's why the answer is C. Larger deflection means more sensitive. You change a bit of current, immediately the scale reading change a lot. So check the gradient of the graph. News flash. This is MCQ. We can flip the X and Y axis. Can flip anytime. Okay? Don't memorize the shape. Learn to analyze the graph. Okay? So first step, I outline the issues with the ammeter. There are two issues. Pointer doesn't return fully to 0. And meter is less sensitive at high currents. So if pointer doesn't return to 0 means when there's no current, still got reading, which is option C and D. I've explained just now. Okay? So when I is 0, there's still reading. the scale reading is not 0. Okay, for both C and D. And then the second issue is large current, less sensitive. Less sensitive at large current. Less sensitive means I need to change a lot, then only the scale will detect. So it's shown by this lah. I change a lot, but the scale only change a bit. We always complain about someone not being sensitive enough. That means you need to actually change a lot of your emotions before the person notices that you change. So I need to change a lot of the current before I get some deflection. Whereas this one, I change the same amount of current, wow, my deflection so big. Okay, so learn to read the calibration curve. There will be this question. Last question regarding the calibration curve. Here we have a digital balance, okay, used to weigh ingredients. In the laboratory, okay, when the weight is applied to the balance, an electronic circuit generates a current, which is then converted to a digital readout on the display. Okay, so if you have no idea what a digital balance looks like, I'll show you a picture. This is a digital balance. When you put whatever that you are measuring on top of it, it will change certain things, certain properties in the circuit, convert it to electrical signal to give you this readout. Okay? So it says here, when the weight is applied to the balance, the electronic circuit generates a current, which is then converted to a digital readout. Beautiful. The electronic circuit gives a current of 2.0 milliampere when the weight 30 Newton is applied. So if I put 30 Newton on the weighing balance, the circuit can produce a current of 2 milliampere. You don't have to care how, don't have to care the design, just take the value as face value. Okay? And if let's say now I decrease the weight to 5 Newton, okay, my current is now 0.5 milliampere. Which calibration curve could represent this circuit? Well, okay, just hang on for a bit. Let me analyze the data first. We have weight, I'll call this W, and then at the same time, we have the current I. So this current is actually, will come out as my weight reading. But it says here when this is 30 Newton, this is 2.0 milliampere. So this is Newton, this is milliampere. I draw a table lah. Okay, so when this is 5, this is 0.5. The first thing I notice is that the ratio is not equal. Because when we transfer from here to here, we divide by 6. Right? 6, 5, 6, 30, correct lah. 0.2 to 0.5, you divide by 4. Oh, what is going on? What is going on? It's non-linear. Non-linear. Okay? So let's look at the graph. Which calibration curve could represent this circuit? So this is what I mean by not all curves are uniform. It may not be a straight line, non-linear. So these are all non-linear. But I noticed that when W decrease, the current should decrease. Meaning when W increase, the current should increase. There are two graphs that I can kick out immediately. For example, this current decrease. Wrong. This one decrease. Wrong. Okay, two more now. Two more. Okay. So one thing we notice is that you can see here, this coordinate gives you your 30, 2. This 32 is for this 30 and 2. Okay. But here there's also another 32. So now we are back to the gradient. Gradient. Which calibration curve will fit this? So I guess the question now is, if let's say I divide the current by 4. So let's do that. Easier to divide by 4, right? So I divide by half by I, and then I divide by 4. So I'm not going to do some bombastic mathematics gymnastics. What I'll do is I'll just roughly split this into 4 portions. Something like that, just roughly judged by all people I. So if I dot, this is my reading. Okay? And what about the second one? What about the second one? For the second one, if you think about it, we are going to split it into half again. Half, half, half. So this is 0.5. This is also 0.5. Dot. Which one looks like 5 to you? Well, this is supposed to be 5. This is supposed to be 5. But also at the same time, this cannot be 5, right? Because here is 15. Halfway mark is 15. You can always measure using your ruler in the actual paper. But even if you judge by eye, like I judge by eye, I think 15 is somewhere here, right in the middle of this axis. In fact, it's a bit closer to here. This is 15. So this one cannot be 5. Question mark, question mark. This is wrong. Okay, so it should be this one. You can just directly see if the value fits the graph. Another way is to actually look at gradient. Okay, so if you think about gradient, right, this gradient, 3 divided by 2, 30 divided by 2, so 2 divided by 30, because can you look at the ratio of I over W? So if I draw another line here, let's make sure it shows on the screen. I draw another line here, and I think about I divided by W. This is just an extra step like if you need it. Okay, I divided by W because I can use this ratio to consider gradient. So the current is I, so it will be 2 divided by 30, whereas this one is 0.5 divided by 5. Which is bigger? Press calculator. 2 divided by 30, this is 0.067, whereas this one is 0.1. So you can tell that when the W increase, okay, there's less gradient. So W increase, gradient decrease. That's how you know it's A. W increase, gradient decrease. Okay, so those are examples about calibration curve. You need to try out some. Okay, so what did we learn today in this video? We learned the difference between precision and accuracy. Okay, so precision is the smallest division that can be measured by your instrument. We can sometimes increase 1 decimal point if we take average. All right, accuracy is how close the values that you measure is to the true value. A good data should be precise and accurate and should have very little error. Okay, so we use the term precision and accuracy to evaluate your data. My data is precise, my data is accurate. Okay, then if let's say it's not perfect, we can always identify errors. Random errors are normally due to human errors. We have done a few examples, and average can improve both accuracy and precision for random errors. But if you have systematic error, you can still take average, you can still take repeated readings, but it only improves precision. It doesn't improve the accuracy because there is a calibration problem. So the second part is I showed you what are the calibration problems that could happen. These are some of them. So if you still treat this graph as a straight line, then you have all sorts of issues. Okay, so I don't want to, spoiler alert, do all the calibration curves questions that are in your past years. There are not that many. Okay, so I'm going to leave that for you to try. And I'll see you in the next video, okay? Hang in there. Bye-bye.